All right, so get this. Today's deep dive is taking us into the world of, wait for it, binary necklaces.
And as simple as they sound, you'll be surprised how deep this topic goes.
Okay.
It's a classic example of elegance and simplicity.
I gotta admit, when I first saw binary necklaces, I pictured, well, actual necklaces.
Right.
And to be fair, that's not entirely wrong, is it?
You're on the right track. We're dealing with a fascinating sequence, A000013, which lives in the Online Encyclopedia of Integer Sequences.
Okay.
The OEIS, for us math nerds.
A library of patterns.
It's basically a giant library of cool mathematical patterns.
You really know how to make a librarian out of me. But okay, patterns.
Yeah.
How do necklaces fit into all of this?
Picture this. A necklace with a specific number of beads.
Okay.
Each bead can be one of two colors. Think black or white for simplicity.
Yep.
A000003 tells us how many unique necklaces we can create as we change the number of beads.
Okay, I'm visualizing it, but there's got to be a catch.
Yeah.
What makes a necklace unique in this mathematical world?
The catch is all about symmetry.
Okay.
Imagine flipping the necklace over like a mirror image.
Right.
That doesn't count as a new necklace in this scenario.
Okay.
It's all about the unique order of the colors.
So if I have a necklace with two beads, I could have black, 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 white, or white, white.
Right.
That's three unique necklaces, right?
Precisely. Now, here's where it gets really interesting.
Okay.
A000013 isn't just about necklaces.
Right.
It pops up in other areas of mathematics, sometimes unexpectedly.
Okay, like what?
One example is the world of computer science, and these things called shift registers.
Wait, hold on. Necklaces and computer stuff. How do those two even relate?
Think of a shift register like a device with n slots, each holding a 0 or a 1.
Okay.
The sequence in these slots shifts with each step, like a loop.
Okay.
Believe it or not, A000013 tells us how many unique output patterns we can get from this looping sequence.
Okay, I'm trying to wrap my head around this.
Yeah.
How can counting necklaces and analyzing these shift registers give us the same numbers? It feels like we're jumping between totally different worlds here.
That's the beauty of it. They are different worlds, but they're connected by this underlying pattern. Think of the necklace as the output of the shift register, where each bead is like a 0 or a 1.
Okay.
Flipping the necklace is similar to switching all the zeros to ones and vice versa in the binary sequence.
So we're essentially counting the different arrangements, whether it's beads on a string or bits in a computer.
Exactly.
That's pretty mind-blowing. And get this, our source material actually lists a bunch of other ways to define A00000013.
Exactly. And that's what makes it so captivating. The sequence pops up in all these seemingly unrelated areas of math, highlighting how interconnected these ideas can be. It's not just one thing, it's a whole web of relationships.
Okay, we've established this sequence is a real overachiever.
Right.
But let's talk about that formula they give us.
Okay.
You know the one, all those Greek letters and symbols?
Right.
It's a bit intimidating, to say the least.
I hear you. It can look a bit like another language. The formula, written as AN, some D divides N, so 2, 2. 2N for N0, is basically a shortcut to calculate the number of unique necklaces or shift register sequences for any given number of beads or stages you want to look at.
A shortcut, huh?
Right.
So what's the magic behind this formula? Can you break it down for me?
Absolutely. Let's take it piece by piece.
Okay.
The N you see there, that simply represents the number of beads on our necklace or stages in the shift register. So the formula calculates AN, which is just a fancy way of saying the number of unique arrangements for that specific N.
All right, that makes sense.
Okay.
But what about the sum D divides N part? Talk about a mouthful.
So that part tells us to consider all the divisors of N.
Divisors, okay.
In simple terms, a divisor is just a number that divides evenly into N.
Got it.
Yep.
So for 6, we'd be talking about 1, 2, 3, and 6, right?
Exactly.
Because those all divide evenly into 6.
Now, for each of those divisors, which we're calling N, we have to calculate this whole chunk.
Okay, I'm trusting you, but that still looks like a jumbled mess to me.
Right.
What are we actually calculating with that?
This is where it gets really neat.
Okay.
That phi phiny,
Yeah.
that represents something called Euler's totient function.
Okay, pause right there.
Okay.
That sounds intimidating.
Right.
Can we get a quick explanation of what that even means?
Absolutely.
Okay.
In essence, Euler's totient function counts how many positive whole numbers are less than or equal to 2π that share no common divisors with 2π other than 1.
Okay.
In other words, they're what we call relatively prime.
Relatively prime. So
Yeah.
they don't have any common factors other than 1.
Right.
Like 7 and 15 are relatively prime, But 6 and 9 aren't, because they both share 3 as a factor.
You got it. And we use this totient function in our formula to essentially capture the idea of uniqueness when dealing with our divisors.
Hold on. How does that tie back to our necklaces? I'm not seeing the connection yet.
Think about it this way. When we're counting those unique necklaces, we're only interested in arrangements that are genuinely different from each other.
Right.
We don't want to count simple rotations as new necklaces.
Right.
This totient function helps us weed out those rotations that are just the same pattern shifted over.
Okay.
It helps us get to the truly unique arrangements.
So we're using this totient function to eliminate those rotational duplicates
Right.
and make sure we're only counting the necklaces that are truly one of a kind.
Exactly.
That's actually pretty clever.
It is, and it shows how elegant this seemingly complex formula really is.
Yeah.
It manages to take all these different factors into account.
Okay, so we've tackled the totient function.
Right.
But what about that tocient part?
Yes,
Does that have something to do with the binary in binary necklaces?
you're spot on. Remember, each bead can be one of 2 colors, so that tocient represents the number of possible color combinations we can have for a given divisor.
Right, because if we have 2 choices for each bead and an n beads in a given section, it makes sense that we'd use 2 to that power.
Exactly. And last but not least, we divide that whole thing by tennis.
Okay.
Why? Well, we have to account for the fact that a necklace can be flipped over.
Right. Yeah.
That flip doesn't create a new necklace, so we're correcting for that symmetry.
Right. We established that early on mirror images,
Yeah.
same necklace.
Exactly.
Okay, let me see if I can sum this up.
Okay.
We're going through each divisor of
Exactly.
using this quotient function to filter out those rotated duplicates,
Right.
looking at all the possible color combinations,
Yes.
and then making sure we're not double counting because of the flip symmetry.
Exactly.
That is a lot to keep track of.
It's definitely a lot to unpack.
Right.
But that's what makes this formula so powerful.
Right.
Captures all these little nuances and gives us this elegant tool to explore A00000001.
It's like a Swiss Army knife of mathematical formulas.
Yeah.
And speaking of tools, our source material mentioned that A00000013 pops up in some pretty unexpected places.
Right.
Something about prime numbers and even cryptography. That feels like a big leap from necklaces.
It does, doesn't it? But the thread connecting all these concepts is actually quite strong.
Yeah.
Remember how we talked about the importance of divisors in understanding this sequence?
Right, yeah.
Well, prime numbers are basically the building blocks of divisors.
Because a prime number's only divisors are one in itself, right?
Right.
It can't be broken down any further.
Exactly. And there's a special type of prime number called a Mersenne prime, which has the form 2 raised to the power of n plus 1 minus 1.
Okay, I'm seeing the connection now. We've got that 2 to the n and n plus 1 in there, just like in our formula.
It's more than just a coincidence.
Okay.
A00000013 has a direct link to Mersenne primes.
Okay.
Whenever we find a Mersenne prime, which is a big deal in the math world, by the way, the nth term in A00000013 will have a specific value related to that prime.
Hold on, so our necklace problem is giving us a way to understand prime numbers. That's wild.
Right.
And what about the cryptography connection? That feels like we're diving into a whole other world of secret codes and spies.
We are, but the basic idea is still the same.
Okay.
We're dealing with patterns and arrangements. In cryptography and coding theory, we use binary sequences, strings of zeros and ones to represent information.
So instead of beads on a necklace, we now have bits of data, right?
Exactly. And A000000 high helps us figure out how many unique code words of a certain length we can create using those bits.
So if we're trying to design a really efficient and secure code, knowing how many unique combinations we have to work with is crucial.
Precisely. And in cryptography, where security is paramount, understanding those binary sequences, like the ones described by our friend A00000013, can be the key to designing super secure encryption algorithms.
Wow, okay. We've gone from something as simple as imagining necklaces to complex codes, cybersecurity, and prime numbers, all thanks to this one sequence. It's like A000013 is this hitter backbone supporting so much of the technology we rely on.
It's a beautiful example of how abstract mathematical ideas, which may seem purely theoretical, can have tangible, real-world applications.
Right.
It just goes to show that math is much more than just formulas and equations. It's a way of understanding the fundamental patterns that govern our universe.
It really shows you how much goes on beneath the surface. We've journeyed from the tangible world of necklaces to the abstract realm of prime numbers and even delved into the shadowy world of cryptography.
And what's remarkable is that these seemingly disparate domains are all interwoven by this elegant sequence. A000013, it underscores the interconnectedness of mathematical concepts, revealing a universe of hidden patterns waiting to be uncovered.
It's like we've been on a treasure hunt, following this mathematical map to uncover these hidden connections. So for our listeners who are now utterly fascinated by the secret lives of binary necklaces, where should their journey take them next? What's the next stop on this mathematical treasure map?
Well, I'd highly recommend venturing into the vast and fascinating world of the OEIS, the Online Encyclopedia of Integer Sequences. It's like a digital cabinet of mathematical curiosities, each sequence with its own unique story to tell. You can get lost exploring the intricate patterns and relationships within these sequences.
It's like a choose-your-own-adventure for math enthusiasts.
Yeah.
You never know what hidden gems you might uncover or what connections you might make. Maybe our listeners will be the ones to find the next groundbreaking application or hidden pattern with implications for fields we haven't even thought of yet. Who knows what secrets are still out there just waiting to be discovered?
That's the beauty of mathematics. The journey of discovery never truly ends. There's always something new to learn, explore, and marvel at. And who knows, maybe one of our listeners will be the one to crack the next big mathematical mystery.